consequences of angular momentum and its conservation. Just look at this dance. Just look at these girls skating, and guess what? Angular momentum and its conservation is behind whatever they are doing. What exactly is the phenomena out here? What has torque or even angular momentum got to do? All of this we're going to see today with me, Shreyas, your physics master teacher at Vedantu, and I'm going live. Hello Paniyam, hello Aishwarya, Ishpreet, his child, practical maths, hi Abhirami. I hope I have answered your question which you had posted in the comment section. Hello Harita, good evening. Hi Chitra, please let us know which account needs to be unblocked. Hi Abhinav, nice to see you all back. And yes, your name is Remo. Remo, you should change your name. And Ankit, I'm not sure if it is buffering, just check your internet speed. And nice to see you back. You have been on and off, these days, but I hope you're doing well, and I hope all things are good on your side, including your studies. So, welcome aboard Dinesh. Good evening, all my warriors. Nice to see all of you in the chat box. It makes my day when I see you in the chat box. And if you are a regular user out here, if you are my regular warrior, then nothing like it. Trust me, you are at the right place. You are in the safest of the hands. And those of you who are joining in for the first time, I am Shreyas. I am the physics master teacher, and I have worked with many offline coaching institutes, many big names that you can think of. And I started my journey more than 10 years back. And many of my students have not just cracked the JEE examination, but they have also secured top 2-digit All India ranks in the JEE examination. So with all this experience comes my confidence, and also the joy of teaching, and the joy that I get when I teach all the students across the country is something which I cannot probably express in words. So make sure you're a part of this journey with me, and I'll be there with you till the end. And for you to remain in this journey, you need to do one small favor. Go smash the subscribe button in case you haven't done that yet, and become a free member of We Enthuse channel, a dedicated English medium channel for all the JEE aspirants, and we prepare you for all the examinations including KVPY and VITSAT. Good evening, all my lovely warriors. Yes, it's a very cool weather out here, and yes, if you are already a warrior, if you are a subscriber, you know what to do. Go smash that like button out there in case you have forgotten to do so. Thank you for the jacket. I rarely wear this, but it seems like it's very cold and I cannot control it anymore. I'm like, okay, I should. I heard in Chennai it's raining a lot, including Bangalore. Some parts of Bangalore it's raining heavily. A lot of places are inundated. I saw some videos of Chennai and Tamil Nadu where, especially Tirupati too, that's in AP, it's completely flooded. Just stay safe, guys, and make sure you have all the contingencies and emergencies at home. Abhinav, yes, definitely. I'll let you know whatever strategy you need to do for your upcoming term 1 examination. Just leave a comment after the video ends. I'll definitely help you out with it. Just mention all your problems. I'll definitely reply to your comment, Abhinav. Okay? Is it true that by just solving easy and medium questions in JEE Advanced, we will be able to get into IIT? Very true, Jaswant. Very true. You have heard it correct. Thank you, Prithvi and Murgesh. I'm so happy to hear that. Hello, Chandan. Hi, Siva Ganesh. Hi Roshni, and you have maths exam, all the best, but definitely watch the replay. I will wait for your comment too. Is rotation going to be completed? Yes, Nanda Kumar, it will be completed this week. Yes, Abhinav, I think I have replied to your comment as well. Oh yes, welcome aboard. Hi Lakshit, welcome back, and you are the 8th grader, I do remember. You're there in yesterday's session as well, I guess. Where do I live? I live on earth, and I live very close to the Bangalore head office. Yep, that's the Vedantu head office. Yep, that's where I stay. Okay, so welcome aboard. Hi Srasti, no problem, practical. We're just going to get started. And yes, I hope you have all smashed the like button. So let's do a quick recap of whatever we have studied today. Till last time. And in today's lecture, we are going to see problems involving torque, angular momentum, and also conserving angular momentum, especially in those problems where collision is involved. By the end of today's class, we would be getting a very fair and good idea of how to conserve angular momentum. And this will help you for the next session, where we are going to have a general discussion, general problem solving on the entire chapter of rotation. So get set, go my warriors. It's time to buckle up. So let's do a quick recap. What is angular momentum? Just like a body which has mass and is moving has linear or translatory momentum, a rotating body about an axis has angular momentum. And how do you define angular momentum? It is the position vector crossed, that is the vector multiplication, with the linear momentum. R cross P or RMV sine theta gives you the angular momentum. Remember this? So M into V is momentum, into R is the position, and sine theta because you have that cross or the vector product out there. So the lecture number 1 is there in the playlist, Pritwan Murgesh. It's moment of inertia, okay, all about moment of inertia. It's all there in the nurture playlist. Exactly, it's the rotational analog of linear momentum. Now the next thing that we also studied was, if it's not a point particle, imagine if it's not a point particle which is rotating around an axis, but a big body which is rotating, then the total angular momentum of such a body is given by not MRV, but a different formula which is I into omega. I hope you remember this. The total angular momentum, instead of mass into velocity giving you momentum, here you have angular mass, which is moment of inertia, into angular velocity giving you angular momentum. So it's all analogous. If you have studied linear momentum, this formula just matches exactly with it. Hi Saja, welcome aboard. If by chance the that body is not just rotating but also translating, then you will have two terms. Remember one thing, whenever you have a particle, you have that formula mr cross v. But when you have a body which is rotating, then you have I omega. What if you have a body which is rotating and translating? Then you have this formula. So this is angular momentum of center of mass. So the entire body is assumed like a point mass. So m is the mass of the body, r is the position of the center of mass, v is the velocity of the center of mass. So this defines the angular momentum of that center of mass, and this term over here is angular momentum with respect to the center of mass, because this moment of inertia is the moment of inertia about the center of mass axis. So I into omega about that center of mass axis gives me angular momentum with respect to center of mass. I'll come to it, practical maths. Just give me a moment. Yep, I do remember all of you. Yep. And okay, so why should we add vector signs above the letters? Because they are vectors, okay, and they follow laws of vector addition. See, if I, for example, if I just write momentum, okay, then it means only the magnitude. It only means the magnitude. But when I put this, then it means magnitude as well as direction. So this means that you need both kinds of information associated with that physical quantity. So when I just say P, I can write 4 kg meters per second. But when I write P bar, I cannot write 4 kg meters per second. I have to write 4 kg meters per second in north direction. Or maybe I can just say 4 j cap kg meters per second. So that's the difference. Is that okay? I hope this is clear. Hi Rudresh. Rajay Pratap, I remember you had a different name. Can you please for one last time tell me your different name, your actual name, so that I remember it forever? Yes. So next thing is torque. Remember, torque was R cross F. Torque is the analogous of force. It basically is the cause of rotational motion. And this is going to play a very significant role in today's class. Keep this in mind. So R is the position where the force is applied, and F is the force which causes that rotation. So the net torque, if at all, if you need to find out, it's nothing but just the addition of all the torques acting on that body. All right. So having said this, let's start with angular momentum conservation. But let me also tell you, just in case if you have a lot of backlogs and if you need help with your preparation, be it the term 1 CBSE board examination, be it KVPY essay examination, be it the JEE Mains and advanced preparation, and even if you think you are late, let me tell you, Vedantu always has your back. We often tell students to join and start preparing as early as possible, be it Vedantu or be wherever it is you are studying. Start your journey early. That is always better and improves your chances for clearing the JEE Advanced and JEE Mains examinations. But by chance, if you are not happy, maybe you have started your journey and you still have backlogs, and if you want a revision plan, then let me tell you, at your fingertips, right on your computer, right on your mobile, you can get enrolled into Vedantu. You get all the features of Vedantu. You don't have to travel anywhere. Vedantu is a completely online journey. Yes, you can kickstart your journey right at Vedantu and just log in, and that's it. Just take up the subscription and you will see variety of tests, assignments, amazing teachers, including my micro courses, all of it at very affordable prices. And you will see packages as low as 1,350 rupees, which has everything. But if you want doubt solving and if you want personal mentorship, then you can go for the plus and the classic version. So per month, roughly the cost is 1,000 chiller rupees. So I think that answers somebody's query as well. Somebody was asking, so what's the approximate price of Vedantu courses? So it's somewhere between 1,000 to 2,000 chiller rupees. You can try it out for even 1 month and see how your journey is going. You can enroll into my courses, and if you don't like it, you're free to leave, but I'm pretty sure you'll enjoy it and you'll continue your journey out here. Now let's also talk about, how angular momentum is related to torque. We just have quickly revised torque. We have revised angular momentum separately, but we are going to see what's the relationship. Glad. Thank you. Funny William. All right. Glad to know that strange 531. I'm so happy, and I really hope you turn this positive energy into results eventually. Yes, I will talk about the homework, and the homework solutions are always there in the PDF, which is there in our Telegram channel. So join the Telegram channel to check out the homework. Okay. So please check it out. Yeah, all the answers and the solutions are mentioned, and I'll read out all the names of the students who have done the homework, somewhere in between towards the end or sometimes at the start of the class. Now, see, we all know that angular momentum is mass into position vector into velocity vector. Let's differentiate this. Okay, this is the vector equation. So let's differentiate with respect to time. So when I differentiate, that means I'm taking the derivative. So it will look something like this. dl vector with respect to time will be, m is a constant, mass of that body, r is the position vector. Okay, so that's also constant. So m r cross, only the derivative will be of velocity. Now we all know what is derivative of velocity. Derivative of velocity is nothing but acceleration. And we all know what happens when you multiply mass with acceleration. This m is a scalar quantity. You multiply it with r or a, it doesn't really matter. So we know mass into acceleration is nothing but force. And we all know what is r cross f. Come on, my warriors, think about it. Oh yes, Srushti. Yes, I'll keep that in mind. Yes, exactly, Chandan, you got it. So r cross f is nothing but the torque. So this is your final expression that we exactly want for today's class. It's going to play a very, very important role in today's class. And let me put this in words for you. So the net torque, okay, sorry, or I would put the net external torque acting on a body or a system, basically acting on a body or a system, is the rate, because dl by dt is nothing but rate of change of angular momentum. So is the rate of change of angular momentum. Very, very important property out here. Also remember one thing, See, if somebody gives you a graph of angular momentum versus time, and let's say they tell you the graph is something like this, and let's say you draw a tangent to that graph. Okay, you draw a tangent to the graph at some point. I don't know, it could be some point where you have drawn the tangent. Guess what the slope of this line will give you? Guess what the slope of this line will give you? Slope is the rate of change of y-axis with respect to the x-axis. Y is L, x is time. So rate of change of angular momentum with respect to time. So I know what this is, dl by dt. It's nothing but the torque. So the rate of change or the slope of angular momentum versus time naturally should give you the torque at that instant. Exactly. So when torque is equal to 0, yes, we are going to come to that practical maths. Very true. Oh my god, Ishika from class 10th, I hope you have watched the previous classes because that will be very much necessary for today's class, but still you can definitely attend and probably revise the concepts later on. Very good. Excellent. Welcome aboard. Okay. So let's get going and let's start solving some questions. And let me tell you, whatever theory I teach you is always there, in the PDF. You can also make notes while I'm teaching. You can also make notes in the recorded form. If you're watching the recorded classes, you can also revise this n number of times before your exam and in general when you want to solve some problems or you want to brush up the concepts. Okay, let's start solving the questions coming up on your screen. Come on, my warriors. A constant torque acting on uniform circular wheel of moment of inertia I reverses its angular speed from omega to the same speed in 4 seconds. The torque acting on it is how much? Satish, how about this? You leave a comment. I'll definitely reply to it. Okay, because I don't want to disturb this flow. Okay, just leave a comment after the video ends. I will get back to you. Okay. Oh my god. So, Sweta, you have class 12 physics MCQ on 25th of November. Okay, is it true for most of the ICSE schools? Do you want me to do something for it? Then I can plan, okay, accordingly. Okay, if there is something that I can do probably, because tomorrow I'm going to have a CBSE mock test for the 12th standard student. If you want me to conduct ISC mock test or something, I'll definitely do it. Hi Charan. Yes. Yep, very true, Ramya. You got it right. Integration and derivatives is nothing but a more calculative, analytical version of graphs. So integration is all about area of graphs. Derivatives is nothing but slopes of graphs. That's it. So, come on. Let's see how many of you can do this. All right. So, the constant torque which is acting on it reverses the angular speed in 4 seconds. So, there was this body which was rotating with omega speed. After some time, the speed has become exactly reversed, but the amount is the same. So, the torque has changed the angular momentum, and let's figure that out. So, angular momentum is nothing but, oh sorry, my bad. A torque, okay, so the torque is nothing but the change in angular momentum upon the time taken. That's what torque is. Rate of change of angular momentum. So the torque will be, change in the angular momentum will be moment of inertia into omega, this is final, minus initial, but keep in mind initial angular velocity is exactly opposite to the final velocity. Remember that because it's given that it has reversed its speed. So that means the initial one will be exactly opposite of I omega. So minus I omega is very important and the time taken is 4 seconds. So this will become 2I omega by 4. 2 and 2 gets cancelled. So it will become I omega by 2, which is option number A. That's it. A lot of people write it as 0. They forget this sign over here. This negative sign is very important because it has reversed. It is basically, okay, I can put it, it is opposite. It is opposite to, final, or final is opposite to initial. Keep that in mind. Okay. So what about using the formula torque is equal to I alpha? Excellent deduction. You can use that formula and you will still get the same answer. Don't believe me? I'll show that to you. See, if you use torque is equal to I alpha, okay, alpha can be written down as change in angular velocity upon time. Correct? Alpha is delta omega by time. Now, what is change in angular velocity? Final minus initial. Now initial itself is minus omega, time is nothing but 4. You will still get this as I omega by 2. Okay, so whether you go by I alpha, whether you go by dl by dt, you have to land at the same place. It's up to you which formula you want to use then, and also you should know all the formulas because all the physical quantities are somehow related to each other. Hi Paulami, welcome aboard. Okay, I think Harita made the same mistake. Great. Thank you, Ishika. Abhishek sir is too good, I know. And all the 10th standard students, especially all of you, I think were studying in the 10th standard under the influence of Abhishek sir. I'm so glad that next year you guys will be studying with all of us and it will be too much fun. Okay, so glad that you are watching 11th standard and 12th standard classes back in 10th itself. It's good, commendable. Moving on to the next question. We have a time varying torque. Interesting. The torque changes with time. You can see 4 into t. T is a variable. That means torque is not constant. It's applied on an object about a pivot. The change in the angular momentum till 3 seconds. Very interesting. Sir, alpha is directly proportional to moment of inertia? No, that's not correct. Torque is equal to I alpha. So it depends what is constant and accordingly things might be proportional or inversely proportional. Okay, coming to this question, torque is given, change in angular momentum is asked. First, let me start with the definition. Torque is dl by dt. Torque is 4t. Interesting, torque is 4t. So this is dl by dt. I want to find dl, but not actually dl, delta L. So I know what to do. And read the question carefully, you will see till 3 seconds. I think there is some history, there is some limits involved, there is some addition involved because every instant different amounts of angular momentum will change. So till 3 seconds, how much is the total change of the angular momentum? So I know what to do. I think I need to shift this dt guy over here, then it will become 4t dt is equal to dl. Why do you think I did this? Is it clicking? Especially if you have attended basic maths class, something should click to you right now. Very good, Chandan. It has clicked to you. Very good, Harita. Perfecto. Proud of you. Really amazing. The reason why I did it is because I can integrate both of them. Now I should add limits. Exactly. I should add limits till 3 seconds. So starting from 0 seconds, time starts from 0 till 3 seconds. Initially, there is no change in the angular momentum. Till the end, you will have delta L as the change in the angular momentum. Okay, so let's see what will the integration result into. The next step will be basically 4 and then you have integration of t dt. T dt's integration is t raised to 1 plus 1 upon 1 plus 1. That means t square by 2. So t square by 2 and I'll put square brackets and I'll put 0 over here, 3 over here. Fair enough. Integration of dl will be just L, square brackets over here, 0 and L. That's it. Those are basically change in angular momentum, upper limit, 0 is the lower limit. Okay, next step, 4 as it is. You have to substitute 3 first and then 0. So 3 square by 2 minus 0 square by 2 is equal to delta L minus 0. So delta L minus 0 is delta L. 4 and 2 gets cancelled, it will become 2. 3 square will become 9. Okay, 9 2s are nothing but 18. So delta L will become 18. And that is option C. Done, done, done. Very good. Excellent. So here in this question, it was not about derivatives, but in fact, it was about integration. And see, nobody can tell you whether the problem is of integration or derivatives just by looking at it. You need to start putting in the values. Like, I first substituted torque as 4t, then I understood, oh, maybe I can put this dt over here, and then it clicked, yes, I can integrate it. Rest all is basic maths which you studied at the beginning of 11th standard. So that's how you found out change in the angular momentum. Beautiful question. Beautiful question. Mona Lisa, if you want doubt sessions, it's all a part of, what do you say, pro subscription. You get unlimited doubt solving, you have doubt sessions, you have tattva discussions, you have teacher connect sessions. It's all a part of, you know, all our long-term batches which are there in the pro sub. So I would definitely encourage you to try it out and enjoy those benefits. Next question. Okay, oh my god, you're from Russia. Oh, that's crazy. Welcome. And I'm so glad that we have also reached the northernmost tips of the earth. Thank you, glad, and welcome all the Russians out here. Thank you, Anjani. And here we have the next question. What do we have? We have a merry-go-round initially, which is spinning in the clockwise direction, and it is traveling and it experiences a positive torque from some uncle. Oh my god, who is this uncle? Uncles are always, you know, up to spinning kids. You visit any park, you will see some random uncle spinning some random kid for no reason. Okay, so this uncle is spinning that person on the merry-go-round, and there is a clockwise torque which are positive, and he applies the torque as shown in this graph. Look at this uncle's torque. So this is the uncle's torque, and uncle starts applying the torque slowly from 0. He increases it till 1000 and then takes it down to 0.9. Interesting. So the question is, how much is basically the change in the angular momentum? And this m was not supposed to be there. Okay, just ignore that. Oh, that is meter and Newton. That's fine. Okay, let's see how to do this. Vulcan. Okay, am I pronouncing the name correctly? Vulcan. Okay, cool. Let's see how to do this. Hi Manojyoti, welcome aboard. Is the ideal gas equation chemistry or physics? It's for both. Okay, you can use ideal gas equation both in both subjects. It's the same thing. It's not going to change. How do we do this? Torque is given as a function of time. If you're thinking about calculating slopes, you are mistaken. You should not find out slope. Be careful. Torque is the slope of angular momentum versus time. And this is not a graph of angular momentum versus time, so be a little bit careful. So, what will we do? Well, I take the hint from the previous question. Remember, in the previous question, torque was dl by dt. Take dt on the other side. So, torque into dt will be dl. Now, just apply integral symbol on both sides. This is torque, this is time. Integration of torque with time. What is integration of anything with respect to anything actually give you? It gives you the area under that graph. Exactly. So if you are wondering what we are going to do over here, we are not going to find out slopes, but in fact we are going to look for the areas under the graph. So torque versus time integration gives me area under torque versus time graph, and integration of dl. Integration of dl is nothing but change. dl. I keep on adding it. It is nothing but the change in angular momentum. Change in angular momentum. That's it. That's what it is giving me. So I know now what to do. Exactly. So I need to find out delta L. So I need to find the area of this graph, which is nothing but area of a triangle. And what is the area of a triangle? Half into base into height, which is nothing but 1000. So 0.9 by 2 is 0.45 into 1000, which is nothing but 450. So 450, is it there? Oh my god, we had E, 5 options. So option D is correct. Excellent, Infinity. Very good, Dakshin, Chandan, Harita. Very good. Proud of you, Polmi. Excellent. So you are seeing so many different kinds of problems right now where torque and angular momentum are related. I hope this has now given you a decent idea of how to solve problems related to torque and angular momentum. Let's scale this up a little bit so that we can move to the next part. Okay. So Gautam, the session started at 7:30. Okay. So every day my classes are at 7:30. Sometimes they are also at 5:30, but usually 7:30. But if you want to make sure that you do not miss any of my classes, there are 2 things you need to do. Join the Telegram channel. Number 2, hit the subscribe and the bell icon, and make sure you choose notify for all the updates. We have a kid and he's doing all kinds of crazy things. The first time the kid is walking out radially. The second time the kid is walking on the merry-go-round opposite to the spin of the merry-go-round. The third time, I don't know, he probably sees probably an insect or something, and he immediately jumps. He immediately jumps onto the branch of a tree and he just grabs that branch. Okay, that's what he's doing. And in the fourth option, he is moving along with the merry-go-round. Okay, he moves on that merry-go-round in the same direction. It's crazy. Hi Akhil, hi Asil. So in each of the cases, what do you think is going to happen? Will the speed of the merry-go-round increase or decrease, or will it remain same? Think carefully and answer. Let's see how many of you can get all the 4 answers correctly. So type it with a comma. Increase, decrease, same, constant, whatever you feel. Okay, so just put commas and put all the 4 answers right in the chat box. Let's see how many of you can get this correct. Come on, my warriors. So first case, he's just walking out radially. Second case, opposite. Third case, he just grabs onto the branch. Fourth case, he's walking in the direction of the merry-go-round. Feel the situation. Put yourself in this kid's situation and think what would happen. Mona Lisa, I'm not sure if it will work out well, because for doubt clearing you need to have a lot of facilities and a lot of spam control and all of that. So that's why we prefer having it on our Wave platform, which is having those capabilities to actually unmute, uncam students and also regulate the chat in a manner which is conducive for the doubt solving. So that's why I say that you should check out the doubt solving in the Pro subscription. Okay, so Ramya saying increase, constant, decrease. Chandan saying same everywhere. Dakshin also saying same everywhere. Infinity saying nothing happens to merry-go-round, we will get hurt. I'm not sure in which cases you will get hurt, but looks like you had a very bad experiences on merry-go-rounds. Somebody clearly does not like merry-go-round in all these things. All right, so Harita saying same in all cases. Dakshin saying torque is 0. Okay, interesting. So very good conceptual question. It's going to just check your concept. Okay, Sundar also saying same in all the cases. Very, very interesting. I don't know. I'm not telling you the answers right now. I'm just waiting to hear all your answers. What happens to the merry-go-round? That's the question. Okay, what happens to the merry-go-round as you do each of these activities? Okay, let's talk about B and D first. They are the most easy ones. Okay, they are the most easy ones. Okay. Just imagine the merry-go-round as a system. What is my system? I'll repeat. My system is not the kid, only the merry-go-round. Merry-go-round. Okay, merry-go-round. And not the kid. Okay, great. When you walk or run this way, okay, when you're running opposite to the spin, where are you pushing the merry-go-round? Think, you are running this way. As you run, you are pushing the merry-go-round backwards, isn't it? So, aren't you actually applying a force on the merry-go-round? You are basically pushing it backwards, this way. You are pushing it back via your legs. What will this force do? I think it will apply a torque. I think it will apply a torque. Yes, Rishik, there is a course starting for 11th. Very soon I'll let you know all the details in probably few days. Just stay tuned. The details are coming very soon. So, because of this force, don't you see there will be a torque on it? And what does a torque do? It changes the angular momentum. Don't you see that? The torque changes the angular momentum. Already the disc was spinning this way. That torque will increase its angular momentum further. So what will happen to the angular speed? So the angular speed will increase. The angular speed will increase. Everybody understood this? Now are you getting the feel of it? So if there is a merry-go-round and if you run for some reason, by some reason, opposite way, the speed of the merry-go-round will increase because you're trying to push it backwards. Okay, so when you run opposite, you're going to increase the speed of that merry-go-round. Very interesting phenomena. Okay, what is happening out here is, I think in option D, he's not running in the direction, or is he jumping out? It looks like he's jumping out of the merry-go-round, but then this situation and this situation looks the same. Then, let's assume that this guy is moving in the direction of the merry-go-round, okay, because then there is no difference between this and this, okay. So let's say if he is moving, okay, let's say he moves along the direction of the spin of the merry-go-round, then what will happen? Again, the same story repeat. He will apply a force this way. So there will be a force this way, and that means there will be a torque like this. And what will this torque on the merry-go-round do? This torque will reduce the angular speed. You can see that because the angular momentum is this way. You can see it is this way. The torque is the other way. So the angular momentum, which is this way, will reduce. Okay, it will not move with same speed. It will reduce. So it will basically, omega will reduce in the fourth case. Is that clear, my warriors? Okay. Now, what will happen when he jumps? Okay, that will come here, or you can also talk about this situation when he's trying to run away from the merry-go-round. So, yes, we are going to come to that, Chandan. We're just coming to that. In this case also, he's exactly jumping. He's jumping up, that's all. So, let's see what happens when he jumps. Now, for some reason, let's say he just jumps, or he just, flies off radially. Okay, he just jumps off radially. Think, when he jumps, where will he apply the force? He'll apply the force downwards, right? When you are jumping, okay, something like this, the force on the merry-go-round will be like this. Will this force create a torque to rotate the merry-go-round? Think carefully and answer, my warriors. When you jump like this, the plane of the disc is this way, merry-go-round. If you jump, the force is downwards. Will this force create a torque this way or that way? Think about it. Will it create a torque this way or that way? No. So if there is no torque, why will the angular momentum change? Hence, omega is basically same, since no torque. There is no torque either this way or this way. Yep. So that force has not created a torque like this or like this. Perfecto, Dakshin, Harita, Sundar, Chandan. This case is special, and that is going to lead us to the next concept. He's on the merry-go-round. He's just running radially. He's on the merry-go-round and he's running radially. This is little bit difficult to analyze because when he's running, okay, he's moving on different circles, and it makes the analysis little bit complicated. So for this scenario, what I'm going to do, I'm going to change my system, and I'm going to, try to understand this particular scenario by assuming both of them as my system. This entire thing is my system. Tell me, the force which the kid exerts on the merry-go-round, is it going to be external force or is it going to be internal force? When the kid runs on the merry-go-round, is it going to be external force or is it going to be internal force? Think for this system. Obviously, these forces which are a part of within the system, they will be nothing but internal forces. And if they are internal forces, the torques will also be internal. So as such, there is no external torque. Correct? So the net external torque, because nobody is pushing right now, is 0. If net external torque is 0, by our previous definition, rate of change of angular momentum is 0. Correct? dl by dt is torque. If torque is 0, dl by dt is also 0. If dl by dt is 0, whose derivative is 0? The variable who is constant, that person's derivative is 0. That means L is constant. Now you'll be like, sir, I got the answer. Angular momentum is constant. So the angular velocity will also remain constant. That is wrong, my dear warriors. That is wrong. If angular momentum is constant, it does not mean, or it does not guarantee, angular velocity will be constant. Reason is, angular momentum is basically I into omega, and this is constant. Now, who told you I is constant? Think carefully, you will realize that actually moment of inertia is changing. Why is it changing? Because one of the particles of that system is actually moving away from the axis. It's not the merry-go-round, but it is the kid. The kid is increasing his distance from the axis. And when you increase r, what happens? R square increases. And when you increase r square, moment of inertia will increase. So, yep, if you have got it by now, I has basically increased, so angular velocity has actually decreased to keep their product constant. Looks very unbelievable, but that is very, very true. You can try this out on a big merry-go-round and you will find that this will always work. Very interesting concept. So because the net external torque was 0, what has happened? Angular momentum's rate of change is also 0. That means angular momentum is constant. But this is angular momentum of the entire system. So what has happened? The kid has moved away from the axis. When r square increases, moment of inertia increases. And when moment of inertia increases, omega should decrease. So angular speed will decrease. Because you have gone on a big circle. You are now going to go on a big circle. Moment of inertia has increased. Angular speed will come down. That's what has happened. Is that understood? Is that understood, my warriors? Is that clear? Okay. Somebody will say, sir, can I apply this principle over here as well? Yes, you can apply. Think this way. The disk was spinning. Take the entire thing as a system. Now, the entire system has an angular momentum. This force will become internal force. This force will become internal force. That means there are no external forces. That means dl by dt is 0. That means L is constant. So the total angular momentum will be constant. Now, if the total angular momentum is constant and one of the entity, there were two things, merry-go-round and the kid. The total angular momentum is constant. One of them decides to go back to preserve, to keep the angular momentum constant. The other one has to increase its speed. I'll repeat, both of them together had the total angular momentum. If one of them decides to go back, then the other one has to increase the speed to preserve the total angular momentum. And that's why omega will increase. Are you able to visualize this? Are you able to see this? Very, very important. Okay. Is that clear? Is that understood? Pakka? Understood? Clear? How angular momentum has been conserved in all these situations. So that leads us to this beautiful example. Look at this simulation. This is a big object, okay? And it's like a contraption. It can change its size. It's right now rotating. It's right now rotating. Now it has some angular momentum. This guy out here is pulling the thread, because of which the contraption, this object reduces in size. This force does not create any torque. Remember, it is along the axis. The force is along the axis, so it cannot create any torque. There is nobody pushing, pulling, twisting it. So there is no torque. If there is no torque, there is no change in angular momentum. If there is no change in angular momentum, I into omega should remain constant. Think what happens when this contraption reduces in size. When all the particles come close by, moment of inertia reduces. Yes, moment of inertia reduces. But I into omega should remain constant. So if I reduces, omega should increase. And that's the reason why when it becomes a smaller object, it collapses, the angular speed increases. Are you able to see that? Is that making sense now? All of you, are you getting a feel of angular momentum conservation? Think about it and put up a yo, put up a smile, put up a thumbs up in the chat box if you got it. Okay, so angular momentum is conserved when the torque acting on the system is zero. So no torque, no change in angular momentum, and it will do all sorts of things to preserve the angular momentum. If moment of inertia increases, omega will decrease. If moment of inertia decreases, omega will increase. If one of the particles decides to go opposite to the angular momentum, the other particle will go faster to preserve the angular momentum. So all sorts of things to just preserve the angular momentum. And this is only true when the net torque is zero. Yes, that's very important. If net torque is not zero, angular momentum is not conserved. Yeah. Okay. The pressure is increased, the pressure will have no effect, Ramya, because it's an internal force. Internal forces, internal torques never affect the total angular momentum of the system. Okay, so that is your angular momentum conservation. Let me put it in words for all of you. I'll repeat it again. If external torque is zero, then rate of change of angular momentum is zero. That means this vector will be constant. Keep this in mind. And that's the principle of angular momentum conservation. When the net external torque on a system is zero, then the angular momentum of the system about that axis is going to be constant. And this is the principle of angular momentum conservation. If you do not believe me, if you're still not convinced, I would request you to do one small thing. Maybe you might have a rotating chair at your house, or maybe at your dad's office, or maybe at the school. Have you seen a rotating chair? Okay, just you need one rotating chair and take 2 dumbbells. What will you take? 2 dumbbells, heavy weights, heavy books, whatever you want. Sit on that rotating chair. Okay, sit on that rotating chair and ask your friend. I hope you all have friends. Just ask your friend to rotate you. Okay, so you will start rotating like this. Now what you do, hold those books or those heavy weights really far away from your axis, and when you're rotating, slowly grab them closer. What do you think will happen next? Put it up in the comment section, put it up in the chat box right now. Those things are very far away. As you're rotating, you bring them close by. What do you think will happen to your angular speed? Will it increase? Will it decrease? Will it still stay the same? Come on, put it up. Waiting for your answers, my warriors. Figure this out. And if you are watching it as recorded, do not forget to post it in the comment section. Okay, correct. Very good, Chandan. Very good, Molesh. Very good, Infinity. Very good, Dakshin. Now you got the feel of it. Try it out and it will work. And that's the principle of those girls who were spinning at the right of the start of the class. I showed you one simulation. So what they are doing is they were stretching their body initially. They had some speed, and when they bring their arms and legs closer, their speed will also change to preserve the angular momentum. This is also the same principle used by a diver. So this is a diving board. This is the water. When this diver jumps from this diving board, he collapses his body. So when you collapse your body, moment of inertia will reduce. You are already spinning, but because you have made yourself small, I decreases, omega increases. So you will spin faster. You will spin faster, and when you think it is the right moment to extend your body again, you extend it so that you dive in properly into the water. Okay, so that's what happens over here when a swimmer tries to dive and rotate himself. He collapses his body to decrease moment of inertia. That means increase omega. So omega increases, and at the right moment you stretch your body so that you land perfectly down in the water. You do not land on your chest or your back, because that is very painful, trust me. How many of you have landed on your chest or your back by mistake, or when you are learning swimming? Put it up in the comments or put it up in the chat box right now. Does it hurt? What was your experience? Please let me know. Let's start solving some questions on this. Yes, ice skater too. Yes, exactly. Hi Neeraj. Okay. So Ramya, I mean, it depends from person to person which is the most difficult concept. Some people feel it is rotation, some people feel it is SHM, some people feel it is electricity and magnetism. It depends. Some people do not like or feel modern physics is difficult. Yep. Or Neeraj has experienced that, and Shivamani too. Yep, it hurts a lot. Let's start solving this question. So we have the earth, and imagine somebody comes and compresses the earth into a smaller earth. That means reduces the size, and in this case shrinks it to half. So the question is, what do you think will happen to the time period of the earth? It's a very interesting question. Now, if somebody shrinks it, okay, you are just shrinking the size, okay, you're not applying any torque. So I can just say angular momentum is conserved, okay, it's conserved, since net torque which is there externally is 0. So what is angular momentum? Angular momentum is moment of inertia into angular velocity. So I into omega will be constant. Now moment of inertia of earth will be 2 by 5 m r square. So this into omega. Now what is omega? Omega is nothing but 2 pi by time period. This will be constant. Now observe this. 2, 5, m, 2 pi, everything is a constant. That means from here we get r square by t is a constant. Very interesting. Now according to the question, r, okay, this r has been made half times. So r square will become half square times. The numerator will change by 1/2 square times. That means nothing but 1/4 of the times. So numerator changes 1/4 times, but the ratio should remain constant. That means if numerator changes by 1/4, even the denominator should change by 1/4. Hence, this will become 1/4 times the previous value. Now we know that the time period of rotation for Earth is 24 hours. So 24 hours into 1/4, that will become 6 hours. So that's our final answer. Interesting, isn't it? Yep. So that's what is happening. So if somebody magically shrinks the earth, the speed of the earth will increase and it will become 4 times more. You'll just have one day which is 6 hours. That's it. 3 hours day, 3 hours night. School classes, everything's less. Even you'll have to sleep less. That will be pathetic. I would prefer to have the earth being slowed down and have longer days and longer nights, more time to sleep and more time to enjoy during the day. What do you guys say? Do you want the earth to spin faster or do you want the earth to spin slower? Let me know in the comments. Let me know in the chat box out there. What is your perception about this? Moving on to the next question coming up on your screen. This is the last lecture, Amir. Yep, this is the last lecture, but we'll have problem solving classes on rotational motion, let me tell you. Yep, very similar to smaller planets. Okay, Roshan, can you just watch it right from the start? Maybe in case you missed some of the starting concepts, and you can also go back in a live session and watch the entire problem right from the start. Okay, let's look at the next question. Okay, so term 1 board preparation, दोनों manage करने में दिक्कत आ रही है Zeph. I would suggest first concentrate on your term 1 and then start with your JEE preparation if you are not confident, and simultaneously solve easy questions of JEE. It will indirectly help you for your board preparation because board also has MCQs at the end of the day. So that's the change pattern. So do more of boards and do easy questions, average questions, simple questions, conceptual questions of JEE Mains. That's what you can do and that will help you a lot. Okay. Now, we have a circular ring of certain mass and radius, and what is happening is it is rotating about some axis. There are two objects attached, and they are placed at the ends of it on the diameter. Then what is the new speed of the wheel with which it will rotate? Hi Yash, you're a little bit late, I guess. Okay, let's try to figure out how to solve this question. First of all, we have a ring. Okay, it is spinning with certain speed omega. The mass of the ring is m and the radius of the ring is r. Now what you do, okay, so this is the axis of the ring. This is the axis of the ring. Now what you do, on that same ring you add two masses, two objects, each of mass small m. So maybe one is over here, the other is over here. This is small m, this is also small m. These are diametrically opposite. This is the axis of the ring. Now this ring will have some new angular speed which is omega f. The question is, what's that new speed just because you place those masses? Again, since you have just placed those masses, you have not given it some push, pull, twist, anything. So since there is no twist, okay, there is no twist or push, that means net torque is 0. That means angular momentum is conserved. That's the starting principle to solve the problem. Let's start from the first diagram because that's the initial situation. This body had some initial angular momentum. So what's the initial angular momentum? Because I'm going to put an equal to, here I'm going to put all the initial terms. Okay, this is all initial terms, and here I'm going to have all the final terms. Initially, it will have angular momentum of, think, it's a ring, it's rotating. Which formula do you use? I into omega, right? Yes, so I into omega, so just use that. What is the moment of inertia of a ring? mr square, correct? So just m, but which m? It's going to be capital M. So capital M, and we have r square into omega. That's it, nothing else. Finally, you have ring and 2 point masses, each at distance r and r. So the new moment of inertia will be moment of inertia of the ring plus small m r square, that's for one mass, plus small m r square. That's the total moment of inertia of the system, and we have omega f. Interesting. Now before we proceed ahead, you can see r square, r square, r square, r square cancels from everywhere. You just have m omega is equal to m plus 2 small m into final angular speed. So final angular speed is m omega by m plus 2m. And is that there somewhere? Yep, I think it is option C. Is that understood? Okay, very good, my warriors. Excellent. Option C is correct. Let's move on to the next one. This is very, very interesting. Okay, this is very, very interesting. Now, the whole idea of angular momentum conservation can be applied to so many different scenarios, but don't get fooled into thinking that just because angular momentum is conserved does not mean energy is conserved. Don't worry guys, if you have some question which is left out, like which books to study for NEET, etc., I'll definitely respond to it towards the end of the class. Just put it up in the comment section. I'll definitely respond. Okay, let's just continue with the flow of the class. So what am I saying? I'm saying that if angular momentum is conserved, it does not mean that energy is also conserved. It may be, it may not be, because they are totally two different things. Energy conservation depends on whether there are non-conservative forces like friction, if they are doing work. So maybe energy is lost in that collision, in that problem, due to some reason. But still, angular momentum may be conserved. Remember, the conditions for each one is different. For energy conservation, you just need to check whether it is elastic collision, whether there are evil forces like friction which are taking away energy. So in those cases, energy will not be conserved. For angular momentum, it's a completely different condition, and that's just if torque is 0 or not. That's it. Let's take up a problem exactly on this. Imagine you have two discs, okay, two discs, and same moment of inertia rotating about their regular axis, the central axis, through the center perpendicular to the plane. Speeds are omega 1 and omega 2. One disk is omega 1, other disk is omega 2. They both are brought in contact with each other face to face with their same axis. Now they will start slipping. They will start slipping. What will be the combined angular speed? That's the question. I'll show the diagram. Things will make more sense after I show you the diagram. This disk is spinning. Okay, this disk is spinning with angular speed omega 1. This is also spinning with angular speed omega 2. You touch them, because of the relative angular speed, they will slip. And eventually, the slipping will cease. It will stop. Okay, they will stop slipping and they will move together with a new angular speed omega. The question is, how much energy is lost in this process? First of all, tell me one simple fact. Why do you think energy is lost in this process? What is that thing which is causing that energy loss? Put it up in the chat box. Ganpati, tomorrow we're going to have mock test of CBSE and we're going to start the remaining part of the JEE preparation, after your CBSE boards end, because a lot of the students have asked for the CBSE preparation, board preparation, ICSE. And so, we want students to concentrate on their boards, and eventually after that we'll have the remaining part of the JEE preparation. Aishwarya saying friction. Very good, Aishwarya. Very good, Chandan. That's right. Friction is causing that energy loss. And to find out that energy loss, I think I need the final velocity. How do I find that final velocity? That's easy. Use angular momentum conservation. That's it. If you look at this entire system, friction is basically internal force. So as such, from the outside, the net external torque is still zero. That means angular momentum of that system is still going to be conserved. It's still going to be conserved. So what is the angular momentum equation going to look like? I omega 1 plus I omega 2. This is all initial angular momentum. Will be together, total moment of inertia will be 2I, because it's given both of them have same moment of inertia. I've assumed it to be I. So 2I into omega. I goes, 2 comes below. So omega will be I1. Oh, sorry, not I1. Omega 1 plus omega 2 divided by 2. But that's not what has been asked. I just have found out one intermediate variable. Oh my God, Infinity, please stay safe, stay inside and take care. Exactly, Srasti. Very good, Shika. Very good. Very good. Yes, that's the friction between the disc. Now, in order to find out that loss, what I'll do, the energy which is lost, which is also the work done, this is only because of the friction. So this is because of the friction. So initially it had more energy. So initial energy will be half I omega 1 square plus half I omega 2 square. Okay, this is basically the initial term, which will be more, minus half new moment of inertia 2I omega final square. That's it. So half I can take common, I also I can take common. So I by 2 is common, and here we have omega 1 square plus omega 2 square minus this 2 will be as it is. Omega is this whole term. So omega 1 plus omega 2 by 2 whole square. Now just solve this and probably we'll get the answer. So let's see what do we get. So I by 2 into omega 1 square. This 2 and this 2 square will become 1 by 2. I can take the LCM later on maybe. So omega 1 square plus omega 2 square minus omega 1 square minus omega 2 square minus 2 omega 1 omega 2, this whole thing. Okay, alright, if you want I'll just put the plus first and then I will do the rest by 2. Okay, so let me do it over here. Okay, let me just use this now. So what will I get? This will be equal to I by 2. Taking the LCM, it will become 2 omega 1 square plus 2 omega 2 square minus omega 1 square minus omega 2 square minus 2 omega 1 omega 2. This whole thing divided by 2. 2 2s are 4. So this will become I by 4. And here we'll have 2 minus 1 is 1. So omega 1 square. 2 minus 1 is again 1 plus omega 2 square minus 2 omega 1 omega 2. Guys, this is very easy now. Okay, I don't need this anymore. What is this? This will be I by 4. A square plus B square minus 2AB. So this will be nothing but omega 1 minus omega 2 whole square. That's it. So that is basically the energy loss. That's the final answer. Done, done. You just have to have that patience till the end, till you complete the problem. Got it, my warriors? Understood? Clear? Let me know if you guys have understood this, all my warriors. Let me know. This is a very good problem which tells you how angular momentum is conserved but energy is not conserved. Okay, so energy is clearly lost. In spite of that, angular momentum is conserved. Yes, that's the answer. Let me also tell you, if you want to win some amazing prizes as well as scholarship, there is an entrance test which is going on in Vedantu, which we call as Vedantu Mega Scholarship Admission Test. Every Wednesday, 8 o'clock. It's for you too, okay, 11th standard, 12th standard students. It's an online test and you will get guaranteed scholarship right from 15% to 100% depending on your scores. So I'm pretty sure you don't want to miss this opportunity. The registration is free and lots of prizes to be won like iPads, Kindles, headphones, bags. You know, it's going to be an objective examination. You can probably take a screenshot of this. This is a paper pattern. It's all, you know, the portions that you have studied. It's going to have, you know, negative marks as well. So be careful. It's very easy to register for this examination. There is a link in the description box. Go ahead, click that link, enter your details, register for it, and make sure you are in that exam on time. Okay. So make sure you do not miss Vedantu's, you know, mega scholarship admission test. Now, the next thing that we are going to see is collision related problems. This is the last part of angular momentum. So till now, you know, things were pretty easy. You're just placing things or things were expanding or contracting and omega changed. But when things collide also, you can apply angular momentum conservation. And whenever you apply this principle or whenever you see rotating bodies collide or something collides and that's when rotation starts, immediately first thing that should come to your mind is probably torque or angular momentum conservation. Okay, so I'll repeat, whenever things collide and they start rotating or whenever rotating bodies collide, then you should always think of torque and angular momentum conservation. Now, some pointers that you should keep in mind, I'll just tell you what they are. First is for linear momentum. Linear momentum means speed. This momentum, linear momentum, translatory momentum, that is conserved only when net external force is 0. So when force is 0, then this momentum is conserved. That's very important. But when torque is 0, then angular momentum is conserved. Do you see some similarities in rotation and translation? In linear motion or translation, when force is 0, momentum is conserved. In rotation, when torque is 0, angular momentum is conserved about that axis. This is also very important that you will not find all the points or axes about which torque is 0. That can also be challenging. You need to figure out about which axis or point is the torque 0. Usually it will be hinge or center of mass or the point of collision or some random point on the ground. That's what you will see. Okay, so remember, whenever you are applying conservation of angular momentum, you always need to find the axis about which angular momentum is conserved. That means where the net torque is 0 and the net torque may be 0 about different axes varying from situation to situation, like hinge, ground, center of mass, point of collision, who knows. Remember, only for elastic collisions you will see energy is conserved. Like I told you before, if there are evil forces or some kind of losses, then you cannot conserve energy. Let's solve two very important questions on this. And I have some very important solved examples for you. This is type 1 problem. I have put it up in the PDF. You need to go through this problem as well as the second type of problem, which also is very important. So these both problems are going to be there in the session PDF. Okay, these are apart from the problems that we are discussing. So very, very important questions which you must go through. But let's solve some good questions as well over here. What do we have? We have a bullet which is moving with very large speed, 500. It hits a disc which is stationary and then it gets stuck in it and they both start rotating together. The question is, what's the angular speed after the bullet gets embedded in it? All the important data are given over here. Let's try to do this question. So first of all, is angular momentum conserved? And if it is, about which axis and for whom? Put it up in the chat box. Whose angular momentum is conserved? About which axis? Why do you think so? Put it up in the comment section. Put it up in the chat box. Think carefully. Even if you are watching it recorded, I would ask you to pause it for a moment, think about it, and then proceed. Come on, my warriors, think. At which axis and for whom is the angular momentum conserved? Is it for the disk, is it for the bullet, or is it for both? And about which axis? Horizontal, vertical? Think about which axis is the torque zero. You might think that, sir, the bullet is applying a torque. Yes, it is applying a torque, exactly, because it is striking it, it is colliding with it. So get rid of that torque. How do you get rid of a torque? Make it internal. How do you make it internal? Make everything as a system. So if somebody considers this entire thing as a system, okay, if you consider this as a system, then this force of collision, this will be internal force, and that means about this axis the net torque is zero, no external torque is there, and that's why the angular momentum of that entire system is conserved. Very, very important. So even after they become one system, okay, the bullet gets embedded, you will see the final angular momentum will be equal to the initial angular momentum. Okay, so Charu, it's not just the disk, because if you take the disk, then there is an external torque. So then angular momentum is not conserved. So that's why disk plus the bullet. That's what is very important. Fair enough. So let's write down the equation. You always start with the equal to, always put initial on one side and put final on the other side. If you think, initially the disk is not rotating, only this point mass is moving. So when I talk about the total angular momentum, it's only the angular momentum of that bullet. And imagine from the top view, this is the axis, this is the disk, this is the bullet which is coming and hitting over here. This is velocity, this is mass, this is R. What do I need? I need R perpendicular. I need R perpendicular to calculate the angular momentum about this axis. From the top view, if you see, it becomes very, very obvious. So the initial angular momentum will only have this bullet term, and it will be mass of the bullet. Okay, so the mass of the bullet into the perpendicular distance of the line of velocity, which is the radius. So I'm just going to assume it as R, into the velocity, which I'm just going to assume it as V, plus 0. The 0 is because of the disk. This is only for the bullet. Is that understood, my warriors? Very, very interesting term. Now the next thing that you're going to do for the final angular momentum, both of them as a system. So find I and multiply by omega. Total I will be moment of inertia of a disk. So m r square by 2 plus a point mass at a distance r. So just small m r square. Okay, I hope this is clear. This is the moment of inertia of a disk. This is the moment of inertia of a bullet. So this will give you total. Okay, so this will give you total moment of inertia into final omega, which is exactly what you need to find. Let's do this. First of all, I think one of the r's will get cancelled. 1 r from here, 1 r from here. So I'll be just left with small m into v is equal to m plus, or m by 2 plus small m into omega into r. One of the r just comes outside. I want to find omega. So omega will be small m into v divided by capital M by 2 plus small m, the whole thing into r. It's just about substitution. Let's do this. Let's just do this. Okay. Oh, कोई बात नहीं दिव्या, देख लो ये problem, and whatever you missed, please watch it in the replay, okay, later on. But watch this. This is a very interesting problem. Mass of that bullet is 2 grams. 2 grams means 2 into 10 to the power minus 3 kg. Velocity कितना है? 500 meters per second. So 5 into 10 to the power 2 meters per second divided by mass of the disk by 2. Mass of the disk is 3.2. So 3.2 divided by 2 plus this mass. My God, it is so tiny. It's a very small mass. I think it is ignored in front of this big one. We have angular momentum conservation problems. Okay, so we are doing collision problems of angular momentum. Into a radius. What is the radius? Is the radius given? Yes, it is 0.5. I think that is also given. Now just solve this. It's going to be easy one. So let's see what do we get. Okay, let's just remove this. Okay, first of all, you can see 2 5s are 10. 10 into 10 square, 10 to the power 3. 10 to the power 3 into 10 to the power minus 3, 1. So this entire numerator will just become 1. 3.2 by 2 is 1.6. So 1.6 into 0.5. 1.6 into 0.5. So basically half of 1.6, which is 0.8. So 0.8 means 8 by 10. That means 10 by 8, which is nothing but 5 by 4, which is nothing but 1.25. So is 1.25 there? Yes, it is. Option A. Done, done, done. So Manikeshav, what has happened? See, this bullet hit the disc started rotating. So I assume the disc plus the bullet as a system, because the bullet's force will become internal force. And then there is no force from outside. So hence angular momentum was conserved. Fine till here. So what is the initial angular momentum? Only of the bullet. It's a point mass. Remember, for a point mass, what is the formula? MRV. So just I have used that formula MRV. Disc is at rest. So no term over there. Finally, when both of them move together, the total moment of inertia. Disc's moment of inertia is half mr square. Bullet is a point mass at a distance r. So mr square. So this total term into omega. Rest is just simplification and substitution. You get the answer. Is that clear? Is that clear? Understood? Okay, Divya, I'm not sure. I think the audio is fine. Just check your internet once, and sometimes it happens, it's a problem from the YouTube side. Just refresh, close the browser and again open it, or open via Chrome browser, or try out Firefox or something else. It works fine then. Very good. So that's how you need to do this. 1.25. Last question on your screen. Okay, last question on your screen. Beautiful question. You have a rod, okay, something like this. It is hinged here. There is a mass which goes and hits it elastically. Yes, elastically. So the question is, so it's not getting stuck. So after that it will rebound. The question is, what is the angular speed after that? A beautiful question on elastic collision and rotation. Think, you have a rod, it's hinged here. This mass goes and hits. This rod starts rotating. Maybe after hitting, this point mass rebounds. Maybe, who knows? So let me just assume the diagram after the collision. This diagram is obviously before the collision. So let me draw a diagram after the collision. So probably it looks something like this. So maybe the rod just started, okay, so maybe the rod just started to rotate. Okay, so I'll just show it omega over here, and this mass, maybe it went down with some new speed. Let's assume the rod's mass is m and the mass is also m. Okay, interesting. So this is also m, this is also m. Very interesting. Okay, now here is what we're going to do. Let me just put a division line so that you're absolutely clear. This is before and this is after. So about which axis and for whom will you conserve the angular momentum? Which axis and for which system will you conserve the angular momentum? It is obvious that the system should be the entire thing. Why? Because if you only choose the rod, then the bullet's force will create a torque. You do not want that. So it should be rod plus the bullet as a system. Make sense? So I will start by saying angular momentum of the rod plus the bullet is conserved. Because I do not want any torques. Internal torques, don't care. Ignore it. Yes, the whole thing. Always, if you take the whole thing as a system, it works. Okay, so don't take individual bodies. Second thing, what is your axis? So for that, think about which axis is the torque zero. If somebody chooses this as the axis, then you are mistaken, my dear friend. Reason is, if you take this axis, the hinge will experience a reaction, sudden jerk. Imagine this is the rod, this bullet strikes. If somebody takes the torque about the center of the rod, do not forget the rod experiences a jerk because of this. So there will be a force that will create a torque. You want to make that torque vanish. So what you do, measure the torque about this axis. So even if there is a force, the torque of that force will be 0. Yes, the torque of that force is 0. Is that clear? So when you measure the torque about this point, there is no torque present at all. So it is conserved about the hinge. I think I gave all these pointers just sometime back in the theory slide. These were very important pointers, tricks, tips, hinge, center of mass. Usually those are the points. Correct. So let's apply that. Remember, always equal to. You always have initial here and you always have final on the other side. So initially, who has angular momentum? Rod? No, it's at rest. This mass? Yes. M, R, V perpendicular. Do not forget to see that V perpendicular out here. This is basically your R perpendicular. Sorry, this is R perpendicular. This is velocity. What is R perpendicular? It is basically the length of the rod. Okay. So the only term that will exist here will be mass of the bullet into L into, what is it? Is it U? Yes, it is U. Why is this 0? This is for the rod. What is this term? This is for the bullet. Is that clear? Is that clear? Is the LHS clear? Why is it 0? It's 0 for the rod. It's not rotating. It's at rest. So this is all before the bullet hits it. MRV, it's only for the bullet. Finally, okay, be careful. The rod starts rotating, and I think you should remember what is the moment of inertia of a rod about the end. The moment of inertia of the rod about the end. So moment of inertia of the rod about the end or that hinge will be using the parallel axis theorem formula, ICM plus M into shift square. I think we have done this again and again. It comes out to be ML square by 3, not ML square by 12. ML square by 12 is about center. ML square by 3 is about the end. Correct. So use that. So this will be nothing but ML square by 3 into omega. But there is this point mass also which is moving. It also has angular momentum, but it is now opposite. Remember, in the first case it was going that way. In the second case it is going that way, the other way. So other way means exactly opposite. So do not forget to put a minus. A lot of people make a mistake by putting a plus sign. Is that clear? So initially it was going like this. The rod is also going like this. This point mass after the collision is going like that. So minus sign. So it will be ML into V. I hope that makes sense. Okay. Okay. I hope this is clear. Now, what you need to do, just simplify this. I think some of the things will probably get cancelled, like M, L, one of the L's and this L. So I'm just left with U is equal to omega L by 3 minus V. I'll just call this as equation number 1. Fair enough. Now, I did not get the answer. What is the question? Question is find omega. You can't find omega because V is an unknown. U is known, omega is unknown, V is unknown. I need one more equation. I did not make use of the fact that it is elastic collision. Where did I use it? So let's make use of the fact that it is an elastic collision. How do I make use of the fact? I know coefficient of restitution is 1. Speed of approach is equal to speed of separation. Yes, a lot of people. I was just seeing that. Dakshin is saying let's use kinetic energy. Very good, my dear friend. Yes, you can use energy conservation, but that will be lengthy because you are going to have square terms. Half I omega square, half mv square. And when you have square terms, it will become quadratic. Getting the roots is going to be a complex equation. I'm going to simplify it without using kinetic energy and just using speed of separation and approach. And you will see that. No, you cannot use speed will get exchanged, Trusty, because one is rotating, one is translating. So you cannot use the concept that the velocities will get exchanged. That also won't work. So the only thing which will work is, okay, so I'll just put it over here. The only thing that will work is relative, speed of approach. The relative speed of approach is equal to relative speed of separation. And let's see what do we get with this. So approach speed. This rod is at rest. This mass goes relatively with speed u. Okay, fair enough. This is just u. Relative speed of separation. Keep this in mind. Separation speed you need to find between the point of collision. This point over here has a velocity of omega L. Omega r. R is radius, omega is angular speed. So one is going down, one is going up. What is their relative speed of separation? The point on the end of the rod, omega L. This bullet, V. So V and omega L. Will it be V plus omega L or V minus omega L? Obviously, it will be V plus omega L. Two things going away. V1, V2. So V1 plus V2 will be the relative speed. So that means it is going to be omega L. So it's going to be omega L plus V. Is that understood, my dear warriors? Is that understood, my warriors? This is nothing but equation 2. I think now I can solve this. I think I don't need this anymore. So getting rid of this. I have two equations. I think I just add them. So taking equation 1 and equation 2 and adding them. U plus U is equal to omega L by 3 plus omega L minus V plus V, that's going to be 0. Minus V and plus V is 0. So U plus U is 2U and this will become 4 omega L by 3. I think one of them will get cancelled, this 2, okay, and this will become 2. So therefore, I'm just going to get omega as 3U by 2L. That's the final answer. What a brilliant question. Did you love it? Did you enjoy it? Wasn't it fascinating? Wasn't it marvelous? Wasn't it excellent? Raghu, we are going to have special problem solving sessions in which we are going to have slipping problems, we're going to have torque problems combined with angular momentum. See, I wanted to do slipping problems as well, but it becomes very exciting when you have angular momentum conservation along with it. So Raghu, just wait for it. Okay, so next session when we are going to solve problems exclusively, you're going to see slipping problems as well. Okay, so this is your first homework question. Put up the answers in the comment section. Second homework question, put up the answers in the comment section again. And the third homework question, again put up the answers in the comment section. This is the third question. And where are you going to get the solutions? In our Telegram channel. So do not forget to join our Telegram channel. Link is there again in the description box below. And who has completed our homework last lecture? Where is it? Where is it? Where is it? I hope you watched my Squid Games class and it was amazing. Okay, so we had rotation. Oops. Yes. Yeah, rotation of rigid bodies and all of that. Okay, so very good. Ishpreet, Harita, Roshni, Chandan, Yash, Srashti, and Remo, Google Nath, good and bold girl. Very good. Congratulations. Good. Keep this up. And there is one more thing that you need to also check in the description box. So for all the students who want to join our pro subscription, remember the link is right over here. Telegram channel link is here and all the links are over here. So the Vedantu Pro subscription link is over here. Click on this link. You will get this page for joining our courses. This is our subscription plan, Lite, Classic and Plus. Lite will give you everything. Test series, live classes, recorded classes, assignments, doubt solving in the class. Classic will give you doubt solving after the class. A lot of you ask for it. Plus version will give you personal mentorship. The courses start for as low as 1,350 per month. And when you use my coupon code, you get that 10% off. So do not forget to use the coupon code and at least try it out for 15 days. You get 15 days extra, okay, free. And the best part is that if you feel like buying the entire course, EMI options are also available. So go ahead, check out this because you're going to find me in the pro subscription and that's what I always look forward to, all of you. All right, thank you very much for joining in today and I hope you had a splendid class. Yes, please hit the subscribe button and also smash the like button down there. Take care. This was Shreyas here. Hasta la vista.